Hi everyone, thanks very much for coming to this session right at the end of the day. My name's Tom, I live in London. I'm a computer scientist and a programmer. A lot of the talks today have been sort of very practical and hands-on, and this talk is going to be a little bit more abstract and a little bit more computer science-y. I think that computer science is fascinating for its own sake, really. I mean, aside from whatever the practical applications of computer science might be, I think it's super worthwhile to understand something about what's going on inside the computer. Like, what is this magic box that we're working with every day, and what are these spells that we're casting on it? And sometimes thinking about that stuff helps me to, when I'm having a bad day at work and my tests are failing, or the asset pipeline isn't working, or whatever it is, I can float off into this slightly more abstract, separate world of thinking about computer science. And it just kind of helps to keep my mind engaged and keep my work fun, even when everything is going wrong like that. So on that note, I want to talk today a little bit about developing an intuition about what it's possible to do with computers, what we can do with computers, and more particularly what we can't do, what it's impossible to do. Just like if you're an engineer, it's important to learn about the laws of thermodynamics so that you don't spend your whole career trying to build a perpetual motion machine. If you're a computer programmer, I think it's important to know the limitations of what computers can do so that you don't spend your whole life trying to get them to do things that they just can't. A friend of mine recently explained to me what it is that he thinks is so good about James Bond movies. And he said the best thing about Bond movies is that in the first 3 minutes before the opening credits, there's like a mini Bond movie. So there's like the cold open, and then you get to see James Bond, and he's kind of infiltrating an enemy facility, and he shoots a bad guy and steals a microfilm and kisses someone, and then he skis down a mountain. And then there's the opening credits, and if you really like Bond movies, then that little 3-minute mini Bond film gets you really excited to watch the whole rest of the film that's about to happen. And if you don't like Bond movies, then in those first 3 minutes, you basically just get the idea. You get all of the good stuff in a Bond movie really quickly, and then you can just kind of zone out for the whole rest of the movie and not really pay attention. And then at the end, when the person you went with asks you if you enjoyed it, you can say, yeah, it was great. I really like that bit where he skied down the mountain. So I'm going to try and make this talk a little bit like that. I'm going to have a little pre-credit sequence to just give you the whole message of the talk in one slide, and then you can just zone out if you're not interested after that. So this is my kind of mini talk right before the opening credits. So if you're only paying attention to one slide, please pay attention to this one. It's tempting to think that we can solve anything with technology and with computers just by applying enough effort and enough ingenuity. But that is not the case. There are some tasks that programs can't perform. And some of those tasks that programs can't perform are very esoteric, and they're not things that you would directly care about. But there are other things that programs can't do as a consequence of the esoteric things. And those other things are very practical and relevant to the stuff that you and I do in our everyday work. So that's it, really. Programs can't do everything. There is such a thing as an impossible program. And then if this was a Bond movie, it'd be like the title sequence now. That's sort of the end of the talk. So if that's all you're interested in, then now you can just zone out and look at, yeah, thank you. You can just retweet, rate me, high rating. It's very concise talk, straight to the point. If you are interested and you want to know more in a bit more detail, then keep listening, and I'm going to unpack that simple idea a little bit and show you some examples of exactly what I'm talking about. So to start showing you what I mean here, I'd like to walk you through how a program can be impossible. And I'm going to explain that by reminding you of two facts of life, two things about the world that we live in that you just can't change. The first fact of life is that we collectively demand universal systems. Now, what do I mean by a universal system? Well, I'll try and explain that by comparing two programming languages. So for this example, I'm going to compare say, Python and Ruby. And by the way, I personally like Ruby, and that's what I use. And in this talk, I'll be using it as a kind of executable pseudocode to explain the ideas. But the specific programming language doesn't matter, and you have my permission to mentally translate the code on my slides into JavaScript or Java or C# or whatever else you're most comfortable with. So it should hopefully be obvious to you that we can take any program written in, say, Python and translate it into Ruby. That's actually pretty straightforward. We can go through a Python program kind of one expression or statement at a time and replace each little piece of Python syntax with the equivalent piece of Ruby syntax. And when we're done with that, we have the original program converted from Python into Ruby. And we can go in the other direction as well. We can take a Ruby program, replace every piece of it with a piece of Python, and then we end up with an equivalent Python program. So in some sense, Python and Ruby are sort of exactly as powerful as each other, right? You can just take a program written in one of them and just mechanically translate it into the other one, and you end up with a program written in a different language that does exactly the same thing. So anything Ruby can do, Python can do, and vice versa. And that's cool. But there's something a little bit more powerful as well, which is that it's possible to write, instead of just translating individual Python programs into Ruby, we can write one special Ruby program that can do what any Python program can do. And what I mean by that is that we could write a Python interpreter in Ruby. So that means that if you've got a Python program and you want to run it on my Ruby virtual machine or whatever, then I don't need to translate it individually into a Ruby program. I've already written a Ruby program that will do what that Python program does. You provide it as input to my Ruby implementation of a Python interpreter, and then my Ruby program that I wrote is going to do whatever that Python program says to do. And again, we can do it the other way around as well. So in both of those cases, we're able to write just this one magical program that is sort of sufficiently general purpose that you can feed it a program written in another language, and it'll just do what that program says to do. And again, there's nothing special about the pairing of Ruby and Python here. I mean, those two languages are quite similar, but you could just as well, write a Python interpreter in JavaScript, or you could write a JavaScript interpreter in Python, right? So all of these languages have got some kind of relationship with each other, which is that you can implement interpreters for one of them in any one of the other ones. And actually, there's a whole constellation of systems that have this property, that if you pick any one of these systems, you can implement another system in it. So I could implement a JavaScript interpreter in Haskell, or I could implement a Ruby interpreter in the Lambda calculus. I don't recommend you try and do that. But all of these systems are sort of implementable in each other. And this is what I meant by universal systems. The property of these systems is usually called universality, or also called Turing completeness. So there's a large number of these systems, and they all share this property of universality. And that's something that we want, because universal systems are able to run software. That's kind of their defining characteristic. And in general, we don't want this situation where we have to make individual programs to do individual jobs, or individual machines to do individual jobs. We want general purpose machines and programs. We don't want to, every time we want to do something different, go to the shop and buy a different box that does it. We want to be able to buy a box that can do anything depending on what input we feed to it. And that's really what's captured by this idea of universal systems, right? We can feed them programs and they can do arbitrary things. The second fact of life is that these programs that I was talking about, these inputs that we can put into universal systems to get them to do anything, these programs are themselves data. Now that will be a fairly obvious statement to anyone who's a computer programmer, and maybe I don't really need to unpack it. But I'm going to unpack it a little bit in order to make my point. And again, I'll be using Ruby as my example language here, but any other language will do. There's nothing special about Ruby. So here's a very simple Ruby program. This is me at the Ruby read eval print loop, just kind of typing in a program. I type puts hello world, and it runs, and it prints out hello world. And that is a program. But another way of thinking about that program is as some data. I mean, what I've done is type in a series of characters. And so actually I can take that series of characters that I typed in, and I can put that just in a string. And so now I've written a different program that sort of got my original program inside it as data. And I don't want to over-egg this. I mean, it's quite an obvious thing that a program is just a series of characters. But the fact that you can take one program and put it inside another one as a piece of data might be obvious to us, but its implications are quite profound, it turns out. If you look at this, you can see that the Hello World program is really just a sequence of characters, a sequence of bytes, really. And inside my programming language, I can investigate that a little bit. I could literally unpack that Hello World program into a series of bytes that make up all of the characters in that program. And as you look at that sequence of bytes, it starts to resemble just one very large binary number, which is what it is really. When a program's written onto the disk, it really is just a long sequence of ones and zeros. And here you can see all of those ones and zeros. And actually, if I concatenate all of those strings together and convert them into a decimal number, then you can see the decimal number that represents this program. And this isn't a reduction of the original program. It is that original Hello World program. I'm just showing it to you in a slightly different way. So in some sense, Hello World is Ruby program number 9796 and so on. Now, if I gave you that number, then I've given you the original program. It's got all the same information as the program I started out with. I could give you that big, long number, and then you could unpack that number into its component bytes, and then you could turn each of those bytes into a character and turn them into a string, and then you could evaluate that string, and you've run the original program that I started out with. Now, some of you might have used these sort of so-called homoiconic languages, like some of the Lisp languages, that have these sort of fancy features that allow you to represent the syntax of programs in the language as kind of first-class data structures inside the language, and they have first-class operations in the language that allow you to manipulate them. And that's a really cool feature, but to a greater or lesser extent, every programming language has this feature. Every program is ultimately just some data, a big number, and every programming language is able to manipulate those things. So the homoiconic languages are just the ones that make this manipulation of programs particularly easy with sort of native features that support doing that. But in any language, you can manipulate programs because they're just numbers. And incidentally, the fact that programs are just numbers means that you can, in principle, enumerate them. Like this is Ruby program number 979 and so on. But you could start out by just generating Ruby program number 1, and then generate Ruby program number 2, and then generate Ruby program number 3. If you kept going like that, you'd eventually generate the next hot asynchronous web development framework, and you'd be able to buy your own island. It would be brilliant. So those two facts of life are, firstly, we demand these sort of programmable, general-purpose, universal systems. They're really useful. And the other fact of life is that the programs that we feed into these things are just data like any other data. And those two facts of life have got an inescapable consequence, which is infinite loops. And I'm not sure that it's obvious how the existence of infinite loops necessarily follows from those two premises. So I'm going to show you how it follows. So just to recap what I just said. Every universal system can simulate every other universal system. So Python can simulate Ruby and vice versa. And the fact that there's this sort of equivalence class of universal systems that can all simulate each other means that each of those systems can actually simulate itself. That's just a special case of any universal system can simulate any other one. And more specifically, every universal programming language can implement its own interpreter. That's essentially what universality means. So if all we know about Ruby is that it's one of these universal systems, if we didn't know anything about its syntax or its semantics, we were just told that it was universal, that it was Turing complete, then that means it must be possible to write some method or function or whatever you want to call it in Ruby that implements an evaluator for Ruby programs. So here I'm imagining that this evaluator gets two arguments. It gets the source code of a program, and then it gets some input that program's going to read on standard input, say. And I don't have time to show you the full implementation of what this evaluate method would entail, but briefly, it would parse the program, so it would take that big string and it would break it down into its component pieces and figure out what the structure of the program was and generate some kind of intermediate data structure, probably an abstract syntax tree. And then it would evaluate that program and sort of buffer up the output of that program. And it would evaluate it probably by walking over that abstract syntax tree. And every time it finds a node that represents some particular operation or instruction, it would actually do that operation or instruction. And it would keep walking over the tree and then going around in loops and doing stuff until it was done. And then it would just return the output that had been sort of buffered up as it was executing all of those instructions, right? Now, this is actually quite easy to implement in a dynamic language like Ruby, because Ruby has got an eval method that lets you just evaluate a string, and you know, you can use the platform that you're sitting on to do the parsing and the evaluation of a Ruby program. But even if Ruby didn't have that eval function, you could still do this yourself, right? Even, you know, Ruby is itself running on a computer program written probably in C, and you could just take all of the logic from that computer program and re-implement it in the host language. So for languages that don't have eval built into them, you could always go to the effort to implement that yourself. So once we have this evaluate method, we can use it to essentially ask questions about programs, and the question we're asking is, like, what would the result of this program be? So I can say, what would the result of this program, which reads a string from standard input and reverses it and prints it out, be if I fed it the string hello world? And evaluate is going to answer that and say the result would be hello world backwards. Now, if we were able to write this evaluate method, which presumably we can because this is what it means for a language to be universal, then we can write another method called evaluate on itself. And this isn't anything special. This is just, instead of being a two-argument function like evaluate is, it just takes one argument and it calls evaluate with that argument twice. So this means, this is asking the question, what do I get if I run this program with its own source code as input? Because programs are just data, right? You can always do that. So I can ask the question, what do I get as output if I evaluate this program with itself as input? And what I get back is, well, in this case, the source code of that program reversed, because what this program does is reverse its input. And if I'm able to write this, then I can write this larger program, which reads a string in, a program in from standard input, and then it evaluates on itself and looks at what its output is. And if the output of that program is the literal string no, then this program prints yes, otherwise it prints no. So you have to focus a little bit here to keep track of what's going on. But I'm going to call this program does it say no.rb. And this is really asking the question of, when I run some program with itself as input, does it output no or not? So, for example, I can echo into it this program and say, when I run this program on its own source code, does it say no? And in this case, the answer is no, it doesn't say no, it just says its own source code reversed. We just saw that. Whereas if I give it this program that prints no if its standard input includes the literal string no, if I feed that its own source code as input, then it will see that its own source code contains the string no, and it will print no. So the answer to does it say no is yes. So nothing I've shown you so far is particularly dodgy, but the dodginess arises when we ask, what happens if we feed this program into itself? It's not actually very obvious what happens if you feed this program into itself. So let's walk through it. So I've got my does it say no.rb, and then I feed a copy of it into itself, and then there are some possible outcomes that could happen. I mean, the two obvious ones are that it could say yes, or it could say no. Now, if it outputs yes, then that means that the answer to the question of, does this program say no when you feed it its own source code as input, is no. It doesn't say no, it says yes. So the answer yes is incorrect here. The answer we were looking for was no, but it said yes. That's not right. So if that output comes out, then that means our program isn't doing what it's supposed to do. But exactly the same logic applies the other way around. If, when we feed this program to itself, the output is no, then the answer to does it say no is yes. It should have said yes. It shouldn't have said no. So that's wrong as well. So assuming that our program is correct, which, judging from what we saw on the previous slide, it seemed to all be correct, neither of those outputs is acceptable because either one of them is giving the wrong answer. So what else could happen? Well, there could be some other output, like it could output the string maybe, but just by looking at the source code of the program, we can see that that's not possible. There are only two things that it could possibly output, and maybe isn't one of them, so that's not right either. So the only other option here is that this program never finishes. It never gives you an answer, either a correct or an incorrect answer, because it just runs forever with no output ever coming out of it. And in reality, that is what actually happens. Although what actually happens is that it will keep allocating more and more stack space until your computer runs out of memory and then everything crashes and it stops, right? But that's not the program's fault, that's the computer's fault. And in principle, we could keep adding more and more RAM to the computer, and this program would keep running and running, and it would be able to exhaust as many resources, as much RAM and time as we were able to provide to it. It could exhaust them and still bust through the amount we'd allocated to it. And that's really what it means for a program to run forever, that it can exhaust all of the resources that you provide to it. So the argument I've just shown you goes like this. Ruby is a universal language, so we must be able to write this method or function called evaluate in it. But if we can write that evaluate method, then we can construct a special program that has to loop forever. That does it say no.rb is built so that when you feed it into itself, it can just keep looping. There's no other thing that it can do that would be correct. And this argument doesn't depend on any knowledge of Ruby or Python or JavaScript or whatever language you're thinking of. You don't need to know the syntax or the semantics of the language, because obviously if you know the syntax of, say, Ruby, you can say, well, I could have demonstrated this much more straightforwardly by just saying, while true, do end or whatever. That's an infinite loop. But you can only write that if you know what the features of the language are. Whereas, I illustrated it with a concrete program, but the underlying argument here is that if you have this self-interpreter, this evaluate function, there's always a way of building this special program that loops forever. So that directly gives us a way to come up with an impossible program, and I'll show that to you now. So these infinite loops that I'm talking about that are an inevitable consequence of universal programming languages are bad. Like infinite loops in the normal code that we write day to day usually indicate that we've made some kind of mistake. That's not the case if you're writing a long-running system like a web server whose whole job is to sit there in an infinite loop serving individual requests. But the code that we write day to day tends to not be those kind of long-running systems so much as we tend to write small algorithmic pieces inside those systems like an HTTP request handler. And you don't want your actual request handler to go off into an infinite loop because that means that the client is never going to be served. So if we don't want these infinite loops to happen when we don't intend them, then we could try removing features from a programming language until there's no way to cause an infinite loop in that language. And this is totally doable. This is just an engineering problem. There's nothing to stop us doing this. So you could take your favorite language and just start crossing out features from it until you've eliminated the possibility of having infinite loops. And just very briefly, you could do that by doing things like removing unlimited iteration. So you could allow you remove things like while loops that just have a sort of a dynamic condition that you're hoping will eventually become false. So you can say we're going to allow finite iteration of bounded data structures and things like that, or between ends of a bounded range, but we're not going to let you just sit in a loop arbitrarily long because you might never stop. You would have to remove the ability to make whatever your programming language calls lambdas or closures or functions or whatever those are. To prevent things like, this is the omega combinator in the lambda calculus, so however you would implement this in your programming language, that's a That's a lambda calculus term that when you evaluate it, it just runs forever. It never stops, so we'd have to rule that out. And that's actually a special case of a more general thing, which is that we don't want to allow recursive function calls. And one way of preventing that, a simple-minded way of preventing it, might be to only allow a function to call another function whose name comes later in the alphabet. So if you have a function called A, it can call a function called B, and then that can call a function called C, but then eventually you run out of functions. So the maximum stack depth of your program is bounded by the number of functions in your original program, and that's going to mean that you also want to outlaw, meta-programming and dynamic function definition and stuff like that. But that's fine. We can take all of those features out. We don't want to allow blocking I/O because we don't want to be waiting for a byte on a network socket that never arrives, and so on. There are a million other things that we need to take out, but you can definitely do this. So we took all this stuff out of your favorite programming language. We'd end up with something called a total programming language. So this is a language where every program is guaranteed to finish executing because you've taken out all of the language features that allow it to sit in an infinite loop forever. Now, if you've got a total programming language like that, let's call that language T, then it must be impossible to write an interpreter for T in the language T. Now, why is that? Well, I've showed you why it is, because if we could write an interpreter for T in itself, then we could use that sort of self-interpreter to construct a special program that loops forever. But this total language that we've built doesn't allow you to write programs that can loop forever, so it must be impossible to write this self-interpreter in this new language that we've come up with. And that's actually really counterintuitive, because an interpreter for a total language is a program that is guaranteed to finish. Evaluating a program in a total language is something that always stops eventually. So that feels exactly like the kind of thing we should be able to write in one of these total programming languages, but we can't. So although a total programming language can express some programs that always finish, it can't express all programs that always finish. And I've showed you at least one that it can't express, which is its own interpreter. Now, that's not to say that we can't write an interpreter for that total language in some other language. We could write it in a universal language like Ruby or Python or JavaScript. That would be fine. We could also write it in some other total language, because then you've got, if we had some other language called U, then we could write an interpreter for T in U, and even if U's a total language, there's no reason why we couldn't write the interpreter in it, because it's a program that's guaranteed to finish. But we just can't write that program in the language itself. So all of that stuff is, to be charitable, kind of mildly interesting. But the question that immediately presents itself is like, how does this connect to reality? Because that total programming language that's had loads and loads of juicy features taken out of it doesn't really sound very much like the kind of programming languages that we actually use. So that evaluate function, the sort of self-interpreter program, is impossible for any total language. So there is no total language that's universal. These are sort of disjoint classes of programming languages. But just like total programming languages have this interpreter program that's impossible for them, universal systems, universal Turing complete programming languages also have impossible programs. It's just that they're a little bit more difficult to see than that interpreter. So let's have a look at some examples of some programs in a universal programming language. Here's a simple program in Ruby. This just reads in a string from standard input, and then it prints that string out. Now, just by looking at this, it should be obvious that this program always finishes. I've got a little asterisk there, and it says, assuming that standard input is finite and non-blocking. So I'm not really interested in the program's interactions with the rest of the system here. I'm just interested in the behavior of the program itself. So assuming that it's always going to be able to read that string from standard input, then this program always finishes. Let's look at another example program. This one reads a string in from standard input, and then it tries to print it out. But before it prints it out, it does this while true do nothing. And just by looking at that, it should be obvious that that program always loops forever, right? It's just going to hit that loop in the middle and then just sit there indefinitely. So these are specific examples of programs in this case, Ruby, and just by looking at them, we can tell whether this program is ever going to finish or not, just by looking at it. But the question is, can we write a program that can decide this in general for any program? So that means, given the source of a program and its input, can we decide whether that program is going to loop forever or not? And that question is called the halting problem, the question of, does a program ever finish? So let's look at some examples to see if we can develop an intuition about how difficult this problem is. Like, is this a super easy thing? I mean, it seemed simple for the two examples we just saw. Is it quite hard? Like, where on the spectrum of difficulty does this problem sit? So here's another example. Does this program always finish? Well, this reads in a string from standard input, and then it initializes a variable n to the length of that string, and then it sits in a loop concatenating asterisks onto some output string and decrementing the counter, and then when n.0 returns true, it's going to print out the output. So this is a program that essentially takes a string and just replaces all of its characters with asterisks. So just by looking at that for a minute, you should be able to convince yourself that that program always finishes. But the reason why it always finishes is quite subtle. The reason this always finishes is that when you call read on standard input, you always get a string object back. And when you call length on a string object, you always get a non-negative integer back. And then when you call -1 on a non-negative integer, you always get another non-negative integer back. And if you do that enough times, you will eventually get a special non-negative integer, which when you call the 0 method on it, is going to return true. So that loop will always terminate, and then you can print it out. So being able to answer yes in this case involves quite detailed knowledge of the semantics of all of these methods in Ruby. So it's not as simple as just glancing at the program. You need to understand what all of these things mean and how they all interrelate, and to come up with an argument about why this program always finishes involves lots of knowledge. So it's clearly not a trivial problem because it involves understanding all of these specific features of the programming language. So let's look at another example. So without focusing on the detail here, this is a program that initializes a variable called n to the number 4, and then it sits inside a loop where it checks to see whether n is the sum of two prime numbers or not. And if n is the sum of two prime numbers, it increments it by 2 and then keeps going. So this program is going to check whether successively larger even numbers are the sum of two primes or not. So it's going to check, 4 is 2 plus 2, and then 6 is 3 plus 3, and then 8 is 5 plus 3, and 10 is 5 plus 5, and 12 is 7 plus 5, and so on. It's going to keep going until it finds an even number that isn't the sum of two prime numbers, and then it's going to stop and print that even number out. And so the question is, does this program ever finish? And the answer is, we don't know. So this program is checking the Goldbach conjecture, which is one of the sort of oldest and most famous unsolved problems in number theory. This was first conjectured in the year 1742, that all of the even numbers are the sum of two primes. Now, this has been checked empirically on a computer for all the even numbers between 4 and 4 quintillion, and they all are the sum of two prime numbers, so it looks empirically quite likely that this is true, but we don't have a proof of it. And that means that it's possible that if you left this program running for long enough, it would eventually find an even number that wasn't the sum of two primes and print it out. So mathematicians have been trying to decide this question one way or the other for over 250 years. If you could write a program that could read this in and tell me whether it was going to finish or not, then I'd be quite impressed. So, and that's not to say that you can't do it. Just because it's difficult doesn't mean it can't be done. But now we're venturing into the territory of being really quite astronomically difficult. You would have to write a program that contained all of modern mathematical theorems and knowledge, and it would also have to have the ability to synthesize new mathematical theorems and knowledge from those existing theorems and keep generating more and more theorems until it found a proof of one way or the other of this. And that is really getting into the territory of being very, very difficult to do. And you're going to win the Nobel Prize if you manage to figure that out. So this is now starting to look like a very hard problem indeed. But maybe it can be done. Let's assume that it can be done. then that means that you can write a program like this, or a method like this. And again, this is just the outline of it. But roughly what this is going to do, it's like evaluate, but this one is just going to, instead of returning a string, it's just going to return true or false and tell you whether a particular program that you passed into it is going to finish or not if it was run on some input. And in particular, we can't just run the program because this halts method has to return true or false. It can't sit there forever. Part of the specification of this thing is that it always gives you an answer. So this is going to do something a little bit like evaluating it. It's going to parse the program into an abstract syntax tree, but then rather than running the program, it's just going to do some analysis on the program and figure out whether it will eventually finish or not, and then it's just going to return true or false to tell you. And again, this is quite reasonable. You can say, does this program eventually finish, this print standard in.read, and then you just come back and say, yeah, sure it does. Or you could say, does this program eventually finish while true do end? And it could come back and say, no, it won't. And you could easily write an implementation of this halts method that gets these two cases right. I mean, you can write an implementation that answers correctly for any finite set of programs because you can just build them into the source code of halts and look them up in a hash table or whatever, assuming you know what the answer is. But if we could do this in general, then we'd be able to take this halts method and we're going to do essentially the same trick as we did with that does it say no program. We could write a new method called halts on itself, which tells you if a program ever finishes or not when it's given its own source code as input. And then we can write this longer program, which reads in a program from standard input. It uses this halts method to check whether this program ever finishes when you run it on its own source code, and then it just does the opposite. So if halts on itself returns true and says, yes, this program does eventually finish, then this one is going to loop forever. And if it returns false and says, no, that program never halts, then this one is going to fall through and immediately halt. So I'm going to call this program doTheOpposite.rb. And as before, the important question is, what does this program do when we run it on its own source code? Now, before we looked at a program that produced output, but this program doesn't produce any output. It's just going to have one of two behaviors. If we take its own source code and feed it into itself, there are only two things that can happen. It can either eventually finish, or it can loop forever. But we're in the same situation as we were with does it say no.rb. If this program eventually finishes, then that means that the answer to the question of what does this program do when you feed it to itself is that it eventually finishes. So what it should have done is the opposite. It should have looped forever because this program is supposed to be doing the opposite. So that's not the right outcome. And the same argument applies the other way as well. If it loops forever, then it should have done the opposite. It should have eventually finished. So that's the wrong answer as well. And what's going on here is that we've designed a particular program, a special program, where neither of the things that it can do is correct behavior, because it's inherently self-contradictory. Now, every program that we write has to either loop forever or eventually finish, but whichever one of those happens in this case, that means that that halts method was wrong about what was going to happen. So by construction of that program that we wrote, we forced that the answer that comes out of that halts method to be wrong, because we're just subverting it. When it returns true to say that the program eventually halts, we just keep looping and vice versa. So because of this sort of self-referentiality, we're able to write a program that does the opposite of whatever this halting checker says it's going to do. So we've sort of caught it in a trap by writing a program that makes it impossible to be right. And this is what the argument looks like. It says, if we could write that halts method, then we could use it to construct one of these special programs that forces that halts method to give the wrong answer in at least one case. But if that halts method gives the wrong answer in at least one case, then it's not a correct implementation of halts, because the correct one would always give us the right answer. So it must be impossible to write that halts method. So depending on how much of that made sense to you, it might be slightly mind-blowing, or it might be completely uninteresting. But either way, it does leave you with the question of, like, who cares? this isn't the kind of thing that actually affects us in our day-to-day life, it doesn't seem like. Like, we never actually want to ask a computer to write a program that will loop forever. I can't remember the last time someone asked me to do that. But we do often want to ask computers other questions about programs. Like when we're writing tests, that's really us teaching the computer to answer questions about programs. And we want that to work. So let's say that I've just started working for a new VC-funded startup in the Valley. My boss has come to me and said that he wants me to write a program that prints "Hello World." I've got a month to do it. I'm going to do it in, we do Scrum and that, so I'm going to, do some iterations and things. And because I'm a software craftsman, responsible programmer, I'm not just going to sit down and bash out this program. That would be ludicrous. First, I'm going to write some tests. And then once I've written my tests, I'm going to write my implementation, and the tests will tell me whether my implementation is correct. So let's say that for my tests, I'm going to write some method like this. This is a prints hello world checker. And I can feed a program into this, and it's going to analyze it and tell me whether that program prints hello world. And I don't know about you, but this seems eminently reasonable. This seems like the kind of thing that it's quite sensible to be able to ask about a program. So if I implemented this, I'd be able to say, does this program print hello world? This program that reverses its input, if I feed it that string as input, does it print hello world? And it would say, yes, it does. Your tests are passing. Whereas if I feed it this program that just upcases its input, and I feed it the same input, it will return false. No, your tests are broken. So that all seems like something we should be able to do in a fair world, but unfortunately, if it was possible to write this prints hello world method, it would also be possible to write this halts method. And I apologize for the Ruby syntax here if you're not familiar with it, but essentially what's going on here is that this halts method builds a slightly larger program from the one that you give it. You pass in a program that you want to know whether that program eventually finishes or not, and then we just build a slightly larger program that will read in that program from standard input and then evaluate that program, and then after the program is evaluated, it prints hello world. And in particular, evaluate here is just throwing away any output of that program. The only thing that this hello world program can do is print hello world, but only after the evaluation of that program has finished. And so once we've built this larger program, we pass it into that hello world checker, and then that will tell us whether that original program finished or not. Because when the original program finishes, then this larger program prints hello world. And if the original program sits in an infinite loop forever, then this one never prints hello world. And this is called a Turing reduction. We've reduced the halting problem to the problem of checking whether a program prints hello world. And that's a bit suspicious, because that tells us that the prints hello world problem can't be any easier than the halting problem, because you can use it to solve, the halting problem. So the argument says, if we could write this prints hello world method, then we could use it to construct a correct implementation of that halts method. But we've already seen that it's impossible to correctly implement that halts method, so it must be impossible to write that prints hello world checker as well. And the source of the difficulty here is that even if a program does contain the command print hello world, to write this checker, you do need to be able to tell whether the execution of that program is ever going to reach that command, which involves deciding whether the part of the program before that command will ever finish, and that's where the halting problem lives. So this is bad news. It means that not only are we not able to ask that very specific program, does this program ever finish, we also can't ask, does this program even do what I want it to do? So you can't ask, in general, whether a program meets its specification, or does this program not contain any bugs? This is a problem that Apple has. They would love to be able to take all of the submissions to the App Store and feed them into some magical machine that tells them for sure whether those submissions are calling any private APIs, or whether they have any malware in them, or anything like that. But in general, that kind of operation is not possible to do correctly. And this observation is called Rice's theorem, which roughly says any interesting property of program behavior is undecidable. And just to tell you the meaning of those words, the word interesting means that any given program may or may not have that property, so it's something that's worth checking for. Behavior, quite specifically, means something about the function that's computed by a program, and that's a bit vague, but it doesn't mean things like syntactic properties of the program. Obviously, you can decide whether the source code of a program contains the literal string foo just by looking at it. But these properties of program behavior are about what happens when the program runs. And undecidable means that you can't write a program to decide it in general. So this Rice's theorem is a massive downer. Like, this is why being a programmer is so annoying. You can't get the computer to tell you things about programs, even though it would be really useful for the computer to be able to tell you things about programs. So, briefly, why does this happen? Why are we in this situation? And roughly, it's because you can't look into the future and predict what a program is going to do in general. The only way to find out for sure what a program is going to do is to run it. And Stephen Wolfram calls this computational irreducibility. The problem is, when you run a program, you don't know in advance how long you have to wait for it to finish. And some programs never will finish. So any system that's got enough power to be self-referential, like these universal systems, can't correctly answer every question about itself. That's the essential content of Girdle's first incompleteness theorem. And this was only discovered in 1936, and it was a massive bombshell in mathematics, and it continues to be a massive bombshell today in computer science, that we can't build these systems that are able to answer every sensible question. In order to answer questions about self-referential systems, we have to be able to step outside of them and use a different, more powerful system to answer questions about the self-referential system. And that was fine in the case of these total programming languages, because we could just say, oh, we'll just step out of it and use a more powerful programming language to answer that question. But the problem here is that when we're talking about universal systems, there is no more powerful system for us to upgrade to. These Turing-complete systems are the most powerful computational systems that we know how to build, so we can't do this step outside to answer the questions. We've hit a kind of a ceiling of capability. So I'm nearly out of time. I'm just going to very briefly try and leave you with information about how we can cope. How do we live in this difficult world? We can cope by asking undecidable questions, but then giving up if we can't find an answer in a reasonable time. So if we want to make a hello world checker, we could just run a program for 10 seconds, and if it hasn't printed hello world within 10 seconds, we can just give up and say, oh, well, if it hasn't printed hello world, then we'll just put it in the no bin. But sometimes that's going to be wrong, because if you just waited another second, maybe it would have printed it out. It might have been one of those programs that prints hello world after 11 seconds. But if you're going to wait around for those ones, then why not wait 12 seconds or 13 seconds or so on? So eventually, you're going to have to accept that you're going to make mistakes. You could ask lots of small questions that collectively provide evidence for the big question that you want. And this is really like writing acceptance tests. You're not trying to prove that a system meets its specification, but you just take a bunch of samples that give you collectively confidence that it does what it's supposed to do. You could ask decidable questions by being conservative, and this is something that optimizing compilers do. They do an analysis called unreachable code elimination, and in order to decide which parts of a program are unreachable, which is an undecidable property by Rice's theorem, they just overestimate which bits of the program are reachable. So by overestimating reachability, sometimes they fail to remove pieces of code from your program that are actually never reached in practice, but for safety, that's a reasonable trade-off. And finally, you might decide to approximate a program by turning it into something simpler and then ask questions about that simpler approximation, hopefully decidable questions. And static type systems are quite a good example of this. If you have a program that talks about values, x equals 1, y equals x plus 2, You could turn that into a much vaguer program about types. You could say x equals some integer, y equals x plus some integer. And by making it more vague, you've made it quite likely that the questions you wanted to ask about it are now decidable in the realm of these kind of vague types. And hopefully, if you've designed your types correctly, that tells you something interesting about the original program. So there is some hope. All right, I'm out of time. If you're interested in this stuff, I've written a book about this stuff. I don't have time to tell you about it, but I go through all of this kind of cool, crazy computation theory stuff. So if you're interested, you should take a look at that. I'm not going to say anything. That's on computationbook.com. There's a free chapter if this has piqued your curiosity. Thank you very much.